right? So I hear that the microphone works. Can I? All right, shall I get started? Yeah. Okay, so let me start with a brief summary of last lecture. So basically what we did in last lecture was to introduce the setting, that's it. The setting we are considering. So we studied stationary currents. Actually, as we saw, we studied the expectation value of any local operator after a bipartite quench. Okay? And in particular, we focus on the limit x position of the observable and t time to infinity, keeping fixed the ratio between these two quantities, which means in Jerome language of last lecture that here we care about only the Euler scale. It's only the Euler scale remains in this limit. Everything else is killed by this particular limit here we are doing. And so we tried to build up our physical intuition for what happens in this kind of problem by considering a free fermionic chain. So a very simple case. And before studying the problem in the free fermionic chain, we had to introduce something about this chain. So we derived the diagonal form of the Hamiltonian. We wrote down the local conserved charges, and we also wrote the eigenstates. So now let me start by building up the last ingredient for our work. So let me consider what I will call the thermodynamic description of the eigenstates. So in the last lecture, we introduced the eigenstates of the model as some states described by a number of parameters, k1, kn. And these k1, kn are quantized. So k and kj is 2 pi over L times some nj, where nj is an integer number, and we choose these numbers to be in the interval minus L over 2 plus 1 L over 2. And so we can picture a state like that basically as a line from minus pi to pi with some holes with some empty spots, which are all the possible values of this. And then we feel only the spots corresponding to the momenta that are actually occupied in the state. Okay? All right. So, but to study the thermodynamic limit when the size of the system here, L, the volume, goes to infinity, it's more convenient to introduce a different description. And the reason is that in the limit L goes to infinity, the number of these holes here, it's increasing more and more, and they are basically getting dense in this interval from minus pi to pi. Okay? So instead of working with these, with the actual momenta, what we normally do is we consider their density. Okay? So we introduce a function of this form. So let's fix, let me do it different. Let me fix L large. So L much larger than 1. And then I introduce this function here. Okay? So this is 1 divided by L times kj plus 1 minus kj. And this defines the function in the point kj. Okay? So this function here is called in many different ways. Here I will call it root density. All right, so the first thing I will show you is that if I consider the expectation value of a two-point function of the fermions, so n1, 2, this thing in the thermodynamic limit is entirely described by the function I just introduced. So to show that, we just rewrite explicitly what these operators here are in Fourier space. And then we can just immediately evaluate this expectation value. And what we get is this. I hope my conventions are consistent. Okay, but now let me here multiply and divide by kj plus 1 minus kj. Okay, all right. So now when I take the L to infinity limit, this difference here, it's getting very small. It's basically going to a differential. Because this is the difference of two neighboring momenta, and these are getting dense. So if I take the limit of this, let me just change my notation for a second. Let me call big N the number of these momenta. So I'm taking the limit of L going to infinity and going to infinity with fixed density. This is the thermodynamic limit, the right one to take. And in this limit, so let me just, I'll write it lim th from now on. So in this limit, this is nothing but where I use the definition I gave you there. Okay? So, what's the meaning of this function? Well, it's the density of these momenta, which means that if I consider 2 pi L times the function in k times delta k. This is giving me the number of occupied momenta in k plus delta k. Okay. Sure.
Can we replace kj by x then from the one line to the other? Like an exponential. The exponent an exponential.
No, I'm just calling this kj is becoming a continuous variable k that goes from minus pi to pi.
That's a k.
That's a k. That's all here. I mean, I mean, you can call it x, but still, it's a continuous variable that goes from minus pi to pi. All right? But, okay. So, and like, what this expression here is telling you is that this particular correlator, regardless of the position of n1 and 2, in the thermodynamic limit is described by this root density. But actually, it's telling you even more, because all other correlators are actually either vanishing or described by the root density again. And this can be seen as follows. So first of all, we note that I said I was calling it 10. All right, and this is very simple to observe because I'm just changing the number of momenta here by 2. And then I'm taking the expectation value on a state that has the same number of momenta as this one. Actually, it's the same state. And that's the same. Here I'm killing 2 momenta on one side. And if I instead consider correlators composed of many of these fermionic operators here, well, these are given in terms of my quadratic ones, because on these states here, I can apply the Vix theorem, right? So I can decompose any correlator, like, well, any correlator of any expectation value of an arbitrary number of fermionic operators, which can be either with dagger, is always written as a linear combination, as a combination of products of correlations involving these quadratic ones. Okay? So in particular, yeah, let me write a simple example just to clarify. For example, let's consider a quartic one, sorry. Okay, so this one can be decomposed in the following way. Here, for convenience, I'm not writing like all these K's all the times. So. Okay, so when you write this combination of products, you should be careful of the signs, but it's not very important to us here, this, so I think this is good enough. But basically the message of all this is that if I give you the root density, then I completely specify all expectation values of local observables. And the reason why I'm saying that is local is because I want this difference here to stay finite in the thermodynamic limit. Okay? So I completely specify the expectation values of local observables in my state. So it's basically the only information you need about the state in the thermodynamic limit. Okay, so there are many comments one can make on this. First of all, note that if I give you a single root density, this corresponds to many, many, many possible eigenstates. So there are many eigenstates that produce the same root distribution, okay? And one of the exercises is actually to show that the number of eigenstates corresponding to rho is at the leading order exponential in the volume. Okay? And actually you can determine this coefficient here, which is called Young-Yang entropy. Okay, so this is times that. I don't have enough space. Okay? All right. So another comment is that to compute the root density, you can actually evaluate the following expectation value. Okay? Where these are the mode operators we introduced last time. So these are C dagger K C K. So the root density is basically nothing but the expectation value of the mode operators. And this is true because we are working with a phrase system. We will see that a similar, like rho, a quantity like rho can be generalized to interacting theories, but you won't have this simple way to compute it. Because basically you don't have the analog of the mode operators in interacting theories, even if the theories are integrable. Okay? The last comment I think I need at this stage is that you can define a root density even for states that are stationary and Gaussian, but mixed. For example, a thermal state. Okay? And you basically use this definition. So if you have a mixed state rho hat mix that is stationary and Gaussian, then you basically compute the root density in the same way. Okay? And note that this is also giving you an immediate way to have a microcanonical representation of this state. So you can replace this state in the expectation value of all local observables by a single eigenstate of the Hamiltonian, which we will call rho. Rho MC. Such that it has the same root density. Okay? So if you produce a state with the same root density, you can basically represent this state. Okay? Good. We are almost done with this part. So the only other important point I want to mention is that if you use this root density, you can compute expectation values. For example, you can compute any expectation values of local observables, and in particular, so also those of charges and currents. Okay? So if you take the charges I wrote in the previous lecture, and you take the expectation value of their densities in the thermodynamic limit, take the expectation value on an eigenstate of the Hamiltonian, of course, then this is written like this. Where this are nothing but 1 square root sine n k square 2 cosine n k. Okay? So note that this set here is a complete set in L2, complete set in L2 of minus pi pi. Okay? Right. Okay? So this is simple because I gave you the expression of this in the previous lecture, but we can actually also compute the expectation value of the currents. So in the previous lecture, I didn't give you the explicit form of the currents, even if it's computable, and I refer to a paper by Maurizio Fagotti, if you want to find it. So Fagotti, J. Fisei, 2016. It's, I mean, it's the only J. Fisei by Maurizio in 2016, so you can find it. I don't remember the number. But, so if you use that expression he gives, or if you compute it explicitly, if you find explicitly the expression, which is not so hard in the free fermionic chain we are considering, then you can find the expectation value of the currents, again, on an eigenstate of the Hamiltonian. Let me use the same notation I'm using here. Yeah. Okay. So you see that the difference between the expectation value of the charge and the one of the corresponding current, with so those that have the same Q1 here, differ only by the presence of this Vk function that I still have to define for you. Okay? So this vk function, in our case, is just the first derivative of the dispersion relation with respect to the momentum k. It's just the group velocity, indeed. And, okay, exactly. So, as you already noted, this can be interpreted as the group velocity of elementary excitations. What I mean by that. So if you have your state psi, characterized by some occupations, as we said before, okay? And you create some excitation of momentum k. So you take something, one of these empty slots, which was empty in the state, you fill it, okay? You compute the energy of this configuration, and you subtract the energy of the configuration without the excitation. Okay, I think then you find just the dispersion relation, because these momenta are totally independent, as we said, since this system is free. Then you can do the same for the momentum. So you can do P of the same thing minus P of the same thing, and you find K. All right? And now the group velocity of elementary excitation is, by definition, Vk, the derivative of this delta energy of K. This is delta P. Okay. So it's basically this. Okay? Perfect. So everything is extremely simple. Yeah, sure. No, I'm saying that if instead of having of being in an eigenstate of the Hamiltonian, you are in a mixed state, which is stationary, so it commutes with the Hamiltonian and it's Gaussian, you can still define a root density for that state. Okay? I told you that if you are in an eigenstate of the Hamiltonian, you can define its associated root density. And here, I'm telling you that actually you can do the same even if you are in a mixed state, if this state commutes with the Hamiltonian and is Gaussian. Okay? Good. So, excellent. So we have everything we need to carry on. And so let's do it. Let's start with our goal. So what we want to do is to find the behavior of all local observables after a bipartite quench in the free fermionic chain, and in the limit x t to infinity, where x over t is fixed. This is position of the observable. Right? So let's get started. So what we do is we initialize, as we said, our system into half chains. separately in equilibrium at temperatures T left, mu left, T right, mu right, which means that we have an initial state of this form. Where again we have this okay. Okay, first of all, it's a very simple exercise, which I leave to you, to show that this rho here is written as the exponential of some quadratic form in the fermions. And you can find this matrix M here very easily. Okay? All right, so, and if you have a state like this, which is written as the exponential of some quadratic form in the fermions, the state is Gaussian in this kind of fermions. So all the correlations can be decomposed using the Vix theorem, as I was saying before. Please. Sorry? It is, well, not in general, no. All right, but it's really simple to write. I mean, it's on the notes. I'm not writing just for a matter of time. So it's basically in some block form. This is 0, this is 0. This refers to the left chain, and this refers to the right chain. It's, yeah, you just like very quick to write. But so I note that Vix theorem holds on this. I mean, Vix theorem for C dagger C, for these fermions. Okay? Good. Now, the second step instead is to evolve with okay, so let's call this step A. Now our step B, evolve with H, that is H right plus H left plus H01 plus h L over 2 minus L over 2 plus 1. Okay? Which is just corresponds to this picture. Okay? Good. And it is very simple to see, again, that if I consider my fermionic operator at time t, so defined in Heisenberg picture in the following way. Okay? So this is again due to the fact that H is again in a quadratic form in the fermions. This is nothing but a combination of these four. So this is n1, this is n0, sum over n0 that goes from minus L over 2 plus 1 to L over 2. Where G is a matrix Okay. So you remember what this notation means, right? It's the sum over these quantized momenta. Okay, so Kn is 2 pi over Ln, and n goes from minus 1 minus L over 2 plus 1 to L over 2. Okay? So this is the sum over all the possible values of this quantized momenta. Okay, so basically this relation is just saying that the fermionic operator at time t is just a linear combination of fermionic operators along the chain. Okay, but this is actually a useful property. Because, again, exercise. Prove that star implies that rho of t is actually exponential form is remaining an exponential of a quadratic form, okay? At each time, where this matrix here is changing. Okay, so basically, this means that Vix Theorem holds at each time. Good? So this means that if we want to compute the expectation value of all possible local observables, we can just restrict to consider quadratic operators in the fermions. Okay, 2-point functions of the fermionic operator. Good. Moreover, due to the fact that since the Hamiltonian and the initial state commute with the number of particle operator, the expectation values of these 2-point functions are always equal to 0 at each time. Okay? So this means we need to consider only this one. Right? And that's what we are going to do. We are going to compute this exactly, at least in the limit. Okay? So now there are, like, it's a lengthy calculation, and I don't want to bore you with all the details, so I will try to jump some steps. But if I'm going too fast, please tell me if you are not following, and I will slow down and explain everything in detail. So the first step of the calculation is to use the relation star, this one, to relate the correlator with the initial one, with the one at time 0. Okay? Good. I'm trying to use the same notation here, not to introduce any typo. I1, I2. G. Star. And then okay? Good. So the second step is some exercise I leave to you, and it's to compute this one.
So these G's are like propagators.
They are like propagators, indeed. Actually, if you have a look to their specific form here, if you plug the dispersion relation, and if you take the thermodynamic limit, you find that they are basically Bessel functions. Okay? So, okay, this is the exercise is left for you. So you should show exercise show that so the question I have for you is, do you have any idea of like how to compute this? Do you know how you would proceed to compute that? I'm waiting for the answer while writing, so please. Sorry? You write this C. You write this C here. You write in the diagonal basis for row. These are all operators, right? Well, I mean, okay. So, okay, and what's the diagonal basis? All right, it's almost done. Okay, so let me define the things I introduced. Can you read it? I hope so. Okay, so I introduce theta, which is 1 if I is in the interval 1L/2, 0, otherwise. Then f right left of k is 1 plus 1 plus left, then it's epsilon of k, mu, right left. Okay, and then I introduce this p, which is 2 pi over L plus 2, n, and n goes from 1 to L/2. And finally, I again use the notation all right, okay. So what's the physical interpretation of all these and how to do this calculation? So basically, the idea is quite simple. You need to express these C operators here as linear combinations of modes of the open chain, right? Because this initial state here is written as the product of two independent open chains. Okay, it's like similar to a Fourier transform, but you have to use modes of the open chain. So, and then instead of exponential phases, you get sines. All right, And then you get slightly different quantization conditions. So here, you see, it's 2 pi over L plus 2n, and n is positive only. Okay? And of course, you get two independent contributions, in the cases where these I1 and I2 are both on the left, so you can have some correlation, and it's given by the thermal correlation on the left, or on the right, and that's the same idea, okay? So it's an independent, and of course, if you take one operator on the left and the other one on the right, at the beginning the chains are disconnected, so there is no correlation, all right? Good. Sorry?
So we still assume some sort of equilibrium or sort of what allows us to like uniform it at least to use the Fermi distribution to the FLR. So like
yeah.
If we can take a statistical average or
It's really, if you take the state I gave you, this is an equilibrium state. You can do the, it's an explicit calculation. We are not assuming anything. We are just doing the calculation. We are assuming, like, the only assumptions we made were in the initial configuration we took. Okay? So we took our system in like two. We take our system made of two separate subsystems, both at equilibrium with different temperatures and chemical potentials. Actually, this calculation can be generalized, but we are considering the simple case now. Yeah. Sorry? Yes, yes. Yes, I mean, yeah, sure. Yeah, I mean, you should have, I'm trying to evaluate it explicitly. Yeah. Yes. All right. So we want the answer, not G. I mean, this is not useful for us. Okay, so good. Now it comes a bit of a technical part. So let me write on this blackboard. We can have a break. Yeah, sure. It's good. No, it's okay. Yeah, it's a new step. So I think we can have a break.